Welcome back to ECE 442-542. Slight change on the process. Please bring a photo ID to exam number 3, and you can have it sitting on your desk if you're coming to the exam. Others, you can read the topics. It's really everything since exam number 2, and there will be maybe a little bit more on the exam than what we covered in homeworks 5 and 6, but it's essentially the PI controller stuff that we have been talking about, and that's really just to get you looking at some slightly different root locus diagrams. So you'll need to be able to do transient performance given settling time, percent overshoot, peak time, and in some cases settling time and peak time may not be given in absolute time. They may be associated with a particular number of samples. If I say give me the sampling or the settling time and I haven't specified a sample period, you have to just tell me, oh, it's going to settle in this many sample periods, maybe 12 or 20 or 40. It won't be a particular numerical value for T sub S. You also need to be able to do a direct design method of Ragazzini, know the 4 constraints and how they are determined. P and PI design and root locus sketching and properties, that goes hand in hand with these P and PI design of controllers. First, transient performance and Z-plane poles. I don't know how many of you have looked at maybe a slight modification, well, an addition to lecture 5.2. I gave one more package of notes. It's lecture 5.2b, and in that packet I provided a performance specification table that essentially gives you ways to find the poles in terms of radius and angle in polar form. Then you can now find these Z sub deltas associated with some radius away from the origin and an angle theta sub d based on somebody giving you a settling time spec and a percent overshoot spec. So you're given R and zeta, or you're given R and theta sub d in terms of settling time and time to peak, or maybe you're given percent overshoot and time to peak. You're given zeta and theta sub d. Now with those 2 parameters, you can now find R and theta sub d. Obviously in the middle row, if you're given the settling time and the peak time, you're given R and theta sub d. Now you can find those pole locations. This first part that I'm talking about really is concerned with how do you go back and forth between what's on the left side of these double barred table and what's on the right side, or can you go from the right side to the left side? You need to be able to go back and forth, and we can do different things by going back and forth in different ways. For example, suppose somebody wants to identify this transfer function g, and now you could view that g as either as T sub c or g, but we're really just saying here's a transfer function. It's second order. Maybe it has a a 0 at the origin, and it might have this structure: a gain alpha z over these 2 pole factors, and those 2 pole factors are associated with complex conjugate poles. Or you could have 2 real poles. But generally when we have some percent overshoot or peak time, we have imaginary components to these poles, and so we have an angle theta sub d. What we're trying to do then in this system identification problem is look at a transient performance response, a step response, and it might not be a unit step response. It might be a response due to an input of magnitude 5 or of magnitude 2, but now you'll obtain this step response curve, and it might be jagged because it's now in discrete time. It's easier for me to just sketch this continuous looking wave, but you can find the maximum value of the output. You can find when that occurred, time to peak. You can find when you get within 1%, and some of these are subjective. You're going to have to just infer what that time is on the appropriate axis. If it is the stair-step pattern, you need to count those steps to figure out when it peaks, and just be clear that sometimes in those steps the system may not start responding for more than one sample period. If you had a pole zero excess of 2, you may actually be locked at 0 for 2 sample periods before you go up. Meaning you might be saying, oh, sample period 1, sample period 2 are actually still at 0, and then I go to 3. So when you're counting, make sure that you're aware that it could be flat down here for more than just one sample period. Look at that distance and see, is that corresponding to one sample period or 2 before you start counting and going further. That's probably the biggest place for an error if you're looking at old exams or practice exams and you're saying, wait a minute, I count 8 steps, why are you saying there's 9, or vice versa. Make sure that we're all counting the same number of steps when it's still locked at 0. You can now figure out, based on that maximum value and the steady state value, what the percent overshoot is, and in that formula the final value, or the y steady state, is in the denominator, so you're comparing the peak to that steady state value. You can now figure out what PO is. Once you have peak time, settling time, percent overshoot, that should give rise to Z delta, and then you can plug that in for these values of R e to the j theta sub d to get the denominator in G of Z, and you may just then say, oh, my numerator of G of Z, I'm assuming, is a constant with a 0 at the origin. What are some of the steps that are involved? Well, you can find alpha, and maybe you'll have to find that later, but you can use this DC gain. What is the transfer function at z equal to 1 going to equal? And then maybe you have that in terms of many different parameters, but once you've found the poles, the only additional parameter that's left is the alpha. But you may have to use this concept a little bit later in the process of solving the solution. That's why I'm saying use this DC gain of your plant to find alpha, but you may have to find that after you've found some of these poles. And you can find the poles several different ways. You can find an angle based on the time to peak. The time to peak is pi over omega sub d. Omega sub d is our damped frequency of oscillation. And we know how that's connected to theta sub d, the angle in our z-plane. Omega sub d times the sample period is theta sub d. You can now solve that for omega sub d, and you can get a time to peak is actually pi t over, theta sub d then is equal to pi t over time to peak. And if time to peak is given in terms of 4 sample periods, or in some of these exams I may say the time to peak is between 3 sample periods and 5 sample periods, I'm meaning it can be equal to or bigger than 3 and less than and equal to 5. So it could live between 3 and 5 sample periods. T sub p then might be 3t, or it might be up to 5t. And that gives you now a range for theta sub d based on what T sub p is. Another performance specification is the settling time. This might be given in absolute terms as T sub s, or it might be given just as number of steps, N sub s. If it's given as T sub s and you have a sample period, you can solve for N sub s. And it's all based on this 1% settling time. In this class, we're assuming settling time is a 1% settling time. That's r raised to the N sub s equaling or less than 0.01. What sample period or value of N sub s gets you less than 0.01 and stays there? You can solve that for r, and doing that, we can take the log base 10 of both sides, take the anti-log again, and you now have r is equal 10 raised to this power of minus 2 over N sub s. That will give you your radius. The only time you can talk about capital R is, in fact, if, or the only time you can talk about a settling time is if your R is inside the unit circle. Your system isn't going to settle if it's unstable. So it doesn't make any sense if you now have found poles that are outside the unit circle and somebody says, what's the settling time? It doesn't settle. It's going unbounded. You can't talk about a settling time if your system is going unbounded. Then there's all sorts of ways to play with the interrelationships of these expressions. The percent overshoot, once you have PO, you can find zeta. And once you have zeta, and maybe once you have R, you can then find an expression for omega sub nt, and omega sub nt is floating around in this theta sub d formula, and you can now find an angle theta sub d if you're just given R and zeta. And if you look at that relationship for theta sub d in terms of R and zeta, you can actually back out R from that and say, oh, if somebody gives me zeta and theta sub d, I can give you the radius. You really have these three shapes, hearts, circles, and wedges, that you are playing with or looking at their intersection. But once you have R and theta sub d, you now have this transfer function g of z. And that could come from settling time, percent overshoot, or peak time. You might want to create a desired transfer function, which we typically call T sub c of z in a Ragazzini design. So now we might want a transfer function that achieves certain performance specifications. A percent overshoot, it might achieve a certain time to peak, and it might achieve a certain settling time. Percent overshoot gives us hearts. That gives us these logarithmic spiral curves, or the zeta values. The time to peak gives us angles. And now you're looking at these intersections, or you could now find a heart, you could find a wedge, and you may need to be on various sides of this heart shape or these wedges, and you're looking at the overlap between those to find this shaded region on maybe one of the first problems on a previous exam number 3 problem. Relative to the hearts, which are red, the wedges, which are green, and the circles, which are purple, here are those different shapes in the z-plane. And now, depending on what you're being asked to do, you may have to shade different sides of these circles, wedges, and hearts to try to find a region that's being specified. If I wanted a faster time to peak, what shape is going to change and how in this plot? If I want to peak quicker, what's going to happen relative to one of these shapes? It's going to be a wedge. So now the wedge is going to change, and how is it going to change? It's actually going to get bigger, isn't it? Theta sub d is going to get bigger. So that angle, that wedge is going to get bigger, or the angle is going to get bigger if you want a quicker peak time, or you want to peak in a shorter length of time. Then that angle, theta sub d, is going to be bigger. And if I say now I want a longer peak time, now maybe you're living below that green line. But you need to get comfortable with sides of these shapes. Am I on underneath? Am I above? Etc. And you might be given a transfer function and say, oh, here's a k, or you might have to find a k, which then will lead to a closed loop pole polynomial, or a polynomial that you can now find closed loop poles with. Once you have those z sub deltas, you better be able to go back to that table and use that to figure out your percent overshoot, time to peak, and settling time. For example, if you're given an r in the z sub delta, that corresponds to n sub s as this ceiling function. If you're given theta sub d, you can now find time to peak is pi t over theta sub d. And if you're going the other way, then you can use them to find r or theta sub d. And finally, if you have r and theta sub d and somebody wants to know the percent overshoot, then you can use many different ways of doing that. You can find the zeta, and in this formula, when you see theta sub d and you're combining it with the natural log of r, you want to make sure that theta sub d is in radians. Or if you do all of these different relationships between r and theta sub d, you can actually find a percent overshoot formula in terms of r and theta sub d directly. And you might just do that to entertain yourself. But here, these are all rules of thumb. Here's the zeta percent overshoot relationship. And if somebody said, oh, I need a 20% overshoot, then you might just say, well, I can quickly find that without trying to compute it analytically on my calculator. I could do a better job of eyeballing than what I did drawing, but you can see that you're about 0.46 for a zeta value. Maybe that's what you use if somebody says, oh, I need a percent overshoot of 20%. And here are the different expressions that we've derived or shown to exist that connect percent overshoot with zeta and zeta with r and theta sub d. And you just need to be comfortable applying these and going back and forth to accommodate either given a settling time or performance specs, then can you find a transfer function, or given a transfer function, can you find the closed loop values, closed loop poles, and then find the performance characteristics. Let's now talk about Ragazzini. And then maybe we'll try to go through one of these as a design, since that was what some of the people asked on the quiz. Or the quiz being, what do you want me to cover in this review session? Ragazzini, you immediately have 4 different constraints or restrictions. R1, R2, R3, and R4. To be consistent, let's try to remember what they correspond to. But in reality, it doesn't matter. You could call R2 constraint 4, for example. But you just need to make sure that you're getting all of these covered. The first constraint or restriction deals with causality. You want your controller, C of Z, to be causal. That just means that it's not going to respond before it gets an input. Or before it sees an error signal, it's not going to be responding. Restrictions 2 and 3 avoid canceling poles and zeros with the controller that you end up designing. Restriction 4 deals with steady state accuracy, and typically that is some relationship on the DC gain. The DC gain could say, oh, I want the DC gain to be 1, but that wouldn't have to be true. You might say, I want a DC gain of 2. But you could still evaluate T sub C of Z with Z equal to 1. There's really just 2 steps to the Ragazzini design. The first step is making sure that you have all of these restrictions satisfied. The second step is really just turn the crank, plug in what you've now determined for T sub C of Z into this formula to find the controller to achieve the performance that you want. Let's look at an example. Suppose now somebody gives you a G of Z that has a 0 at 1/2, a pole at the origin, and a pole at 1. And mentally you might be, and I might even just sketch quickly the pole 0 pattern so that I can kind of see what I have for G of Z. And a lot of times on the homework I said, make your closed loop system have a deadbeat response, but that's not necessarily always going to be the case for a Ragazzini design. If you want some other performance, maybe you want a given settling time or a particular peak time. That now gives you a Z sub delta. Remember what we just talked about. Translating performance specs to Z deltas. Now, instead of having all of your poles in T sub C of Z at the origin, you might have your dominant poles determined by performance specifications. So you now have a Z delta as a complex conjugate set of poles. And I would suggest that you look at problem 2 in some of the previous exam 3s, and in particular the one just last year, to see an example of that. Now that example may not go through the whole process, so make sure you read the exam question carefully. It may just say, find T sub C of Z that satisfies these constraints or these requested performance parameters or performance specifications. I have this double-headed arrow with a question mark. What does that Z minus 1 factor in this expression in the denominator for G of Z? What does that provide for me? Does that give me anything? Is there anything valuable coming out of that? Open loop pole at Z equal to 1. It's right on the stability boundary. How can that but that's consistent with steady state accuracy that we were getting with a PI controller. Having that pole factor, or that pole at z equal to 1, ensures that if you can stabilize the closed loop system with this plant, no matter what your controller is, you're going to have, if your closed loop system is stable, you're going to have zero steady state error due to a constant reference input. If you put in a reference of 4, you're going to go in, after the transients have decayed, your output will be 4 because you have a pole at z equal to 1. You have that factor of z minus 1 in the denominator of your plant. It doesn't just have to appear there due to a PI controller. Oh, so what if we attack this problem with the following goal? Our closed loop system has deadbeat response. What does that mean relative to T sub c of z? What's our desired closed loop transfer function look like, or in particular, what's its denominator look like? What can we use this based on that plant? Can we use T sub c of z equal to k over z if we start with this g of z? What are our restrictions or constraints? Restriction 1. What does it say? That's concerning the pole zero excess of our desired closed loop transfer function. It has to be at least the same as the pole zero excess of our plant. What's our pole zero excess of this plant? 1. What's the pole zero excess of this T sub c of z? 1. So we've actually satisfied restriction 1 with this. Now, whether we can keep going or not, let's see. What about restriction 2? Restriction 2 deals with what? We're looking at unstable zero factors. Do we have any unstable zero factors in this g of z? Do we have any factors in our numerator that correspond to values, or that have values of z outside the unit circle? No. So restriction 2 is not even applicable. So all of these restrictions may not need to be satisfied for all problems. What about restriction 3? Restriction 3 deals with poles outside the unit circle, and really I should say on or barely inside. In this case, let's just agree that on or outside is what we need to worry about. So yes, restriction 3 does come into play because we have a pole right on the boundary. So now what do we want based on restriction 3? Restriction 3 says that we want the zeros, or we want this expression evaluated at the unstable pole, which is at z equal to 1. We want that to be 0. And what about restriction 4? What was our goal All we said is we want a deadbeat response. We didn't say anything about steady state accuracy, did we? So that wasn't even a part of our specification. So this was no steady state error specified. We don't need to worry about that, but it will be giving us zero error due to a constant input just because we had a pole at z equal to 1 in our plan. So let's now go back to the one that needs to be maintained, which is restriction 3. And this says that we want 1 minus t sub c of z at z equal to 1, or maybe I should, doesn't really matter. We want that to equal 0. And we have picked already a structure for t sub c of z of k over z. If we evaluate that at z equal to 1, then we plug in z equaling 1 in the denominator, and we want that to equal 0. That now forces a value on this yet to be determined parameter k. If we want 1 minus k to equal 0, k needs to be 1. In order to satisfy restriction 3, now we've figured out that t sub c of z equaling k over z with k equal to 1, this is now our desired closed loop transfer function. Let's return to restriction 4. We don't need to, but we can see, hopefully, that since the open loop pole at z equal to 1 in the g of z there will be what kind of an error to a constant input. What's our error going to be if we can stabilize the system? And is t sub c of z, is our closed loop system stable based on t sub c of z? Where are our poles? Hopefully they're going to be inside the unit circle, and yes they are. We have one pole at the origin. What do we know about the steady state error if we put in a constant input? An input of 10, an input of 7, an input of 6. Our output's going to go to 10, 7, or 6. We're going to have 0 steady state error because we had that pole at z equal to 1. So now we can do step 2 of this direct design by Ragazzini. Just turn the crank on this formula. 1 over g of z, t sub c of z over 1 minus t sub c of z. Let's do that second bracketed expression by itself. And t sub c of z we found was 1 over z, 1 minus 1 over z. Or now all of that t sub c over 1 minus t sub c boils down to 1 over z minus 1. We can now use that in the c of z expression. This is 1 over, and what was our g of z? That was z minus 1/2 over z times z minus 1. And we now multiply that by 1 over z minus 1. That z minus 1 is in the right spot to be canceled by that z minus 1 factor. And the z in the denominator of the denominator comes upstairs, and we now have a z minus 1/2. That's our controller to achieve the desired specifications that we want, or in a block diagram, there's our C of z. Our plant and we have a lot of cancellations happening. We have this factor canceling that canceling that, and now we're left with a pretty simple block diagram. We now have boiled this down with the plant controller combination we have in the forward path, 1 over z minus 1. In this closed loop configuration. Now that we have that, we can use our T sub c of z formula if we wanted to. We know that that's 1 over z minus 1 over, so it's g bar over 1 plus g bar. And what have we found? Yay! That's exactly what we said we were going to achieve. We said our closed loop transfer function was going to be 1 over z, and in fact, with that controller and plant combination, it indeed was. And what did we do? We really canceled a pole at the origin and a 0 at 1/2 with our controller to give rise to this closed loop transfer function of 1 over z. What does that C of z actually look like in terms of implementation? This was now what happens when we put in the air signal E of z and get the output U of z. This is now z over z minus 1/2. If I want to write that in terms of z to the minus 1 operators, I can multiply it by 1, or I now have 1 over 1 minus 1/2 z to the minus 1. And can you take that into the time domain? Now my controller is simply saying, oh, I want to take the last control signal that I put into the plant and scale it by 1/2 and add that to the present air signal, and this is now my implementation of the controller. And you probably could code that up in a processor to generate the controller that you need to control that original system. This is the implementation. Or what you might refer to as the realization of that controller. And if you had a different set of performance specifications, instead of saying you want your system to have a deadbeat response, that would now impact what T sub C of Z looks like. But once you found T sub C of Z and satisfied all of these restrictions, you turn the crank to generate your controller. And now if somebody says, well, I need you to implement that controller, you now know how to do that. You know, C is just U over E, and you can now put that into the time domain and say, oh, here's the difference equation that you need. Measure the error, have the input to the plant in a memory location, and combine them in this way, and that's now the input that you apply to your plant. And your closed loop system will behave as if it was this 1 over Z. Let's look at some root locus patterns. Suppose I have a pole there. Actually, no, that's not what I wanted. What if I had a pole here? What's the root locus of that? This is a pretty easy root locus. Is there any value of K or any range of K that will stabilize that system? The red line indicates the closed loop poles, the possible values of your closed loop poles. Hopefully you can see that you need to crank up the gain a little bit, because open loop, this is unstable. Your pole's outside the unit circle. You need to get it beyond that triangle. So this would be now K triangle is your minimum value. And this would be K when Z is equal to 1. And your maximum would be the value that pushes you outside the unit circle at the left, or goes just beyond -1. So this is now K max, or K box. This is now K with Z equal to -1. And stability is given by K between delta, K delta, and K box. What if we had a root locus for that pole zero pattern? Pull out your knife and cut up your bread. How many segments do you have, real axis segments? And how many belong to the root locus? Hopefully you can see that right there is your root locus, and now that's a pretty trivial closed loop system. What if you now had pole zero patterns? Let's say this is now 1 and this is -1, and maybe you had a pole here and a 0 here. How many real axis segments exist, and how many belong, or which of those belong to the root locus? Is the segment from the 0 to plus infinity, is that part of the root locus? No, we have no poles and zeros, let alone anything odd. Our root locus is between that pole and which direction do I locate my arrow? Does the arrow point right or does it point left? It goes from the pole to the zero. And now do you see that, in fact, I've kind of flipped this on its head in terms of where I evaluate z to find the minimum gain and where I evaluate z to find the maximum. There would be k-min, and that's now going to be k when z is equal to -1. So those rules for finding the minimum and the max, you want to make sure that you're looking at what's happening, and this would now be k max when k is equal to, or evaluated at z equal to 1. What if I gave you this pattern and I said that pole was at 0.8 and that pole was at 0.2? What's the root locus look like here? Now we can do our cheer, can't we? We can put our hands together. They're going to be touching each other halfway between at the midpoint of 0.2 and 0.8, which occurs where? They're separated by total distance of 0.6. It's going to be halfway between. So 0.3 from either one, which is now at 0.5, and then it goes up and down. And this is now occurring. That breakaway occurs at 0.5. And you now have two branches going off to infinity, where one of the infinities is 0.5 plus j infinity, and the other one is 0.5 minus j infinity. What's the range of k for stability, or is this always stable? And can you find the k or range of k for stability? If nothing else, you could simply draw a unit circle and say, whoops, those branches do leave the unit circle, so there is a limit on how much I can crank up k. Can you actually find that value at the box? Do we have any information on z sub box? We have its real component. It's 1/2. So we now know that this is 1/2 plus j, let's say y. And we know that that's right on the unit circle, so we know that this hypotenuse has a length of 1. And that's how we could find y. We now know that a squared plus b squared is equal to 1, and we know a is 1/2. Or b is now the square root of 3 over 2. And now you know that z box is equal to 1/2 plus j square root of 3 over 2. And what's the k to get us to that box? Can we find it, or do we have enough information? Trick question. I've already scared some people. They had to leave. Since I scared those people, I'm not going to whisper in anyone's ear again, I guess. But I didn't give you all the information that you really might need. I didn't tell you the magnitude of the numerator in this transfer function. I just told you the poles. If you said g of z is now z minus 0.2 and z minus 0.8, I didn't tell you what was up there. I know there's no z, but I didn't tell you the gain, did I, or the constant. Suppose we just assume that that's 1, but you wouldn't want to necessarily just put a 1. You would say, I'm assuming that value is 1. Now can you find the gain k? Now you can, because you know from the magnitude condition you have kg of z is equal to 1. And this now says that k times 1 over the magnitude of z minus 0.2, z minus 0.8 is equal to 1. Or k is now equal to z minus 0.2, that magnitude, and z minus 0.8, that magnitude. And if you wanted to find what the value is at k box, is that what it was? So the z, well, I didn't box it, so let me just say z is now 1/2 plus j squared or 3 over 2. You plug in that value of z, and both of those magnitudes are going to be the same, so you just have to really evaluate for one of them, and then square that value, and you have k box. Or stability now. Looks like that. What if you had that pole zero pattern? What's the root locus look like there? That's our running joke, isn't it? Two poles walk into a restaurant. You have two poles to the right of a 0. Two real poles to the right of a 0. And in fact, you can extend this a little bit. If you now had a 0 here and you had complex conjugate poles, if you find that, that's now the radius, and that radius now can be used to find the reentry. Do you have a breakaway in that right plot? There is no breakaway, but there is a reentry. And you could find that reentry point by finding the radius between the center of that circle, which is the location of the 0, and one of those poles. Those poles are complex conjugates. You just need to find that radius. That radius now is to the left in distance from that 0, and that will give you the re-entry point. No breakaway, but now we have Z re-entry. Going back to the left, we now have our pattern that you're going to get tired of me talking about, but there's your 2 real poles to the right of a 0. And this radius is based on those 2 distances, L1 and L2. Suppose your unit circle was right there. Is that system stable? No, there's no way. You need, how many branches do you have on your root locus diagram with the one on the left or the one on the right? How many branches? 2. And no branches in the one on the left are ever inside that yellow unit circle. What if you had a unit circle that was given by the blue circle? Is that now stabilizable? Can that system be closed loop stable? The blue. So how am I going to do this? Let me say yellow. Never stable. Blue. Is that stable? Closed loop stable. And what are you looking for? You have 2 branches. You need both branches to be simultaneously inside that blue circle. That's not happening either, is it? That's never stable for the blue circle. Am I out of colors? Nope. What if my unit circle, didn't really want to make it that big, was like that? Boy, that's getting pretty messy, isn't it? Is that ever stable? Does it ever become stable? You want 2 branches to simultaneously be inside the magenta. That pole, the far right pole, if we crank up the gain K, eventually it will go inside, and it will go inside, and the one on the left is still not even to the breakaway point, is it? Which means that this rightmost location right here could be the minimum K for stability. And just assume that this is symmetric in the conjugate sense. Am I stable if I keep K bigger than K min? Am I always stable for K bigger than K min? See some heads violently shaking right to left. Wish my head went that easy. Today I'm going to have to do some angles, loosen up. Where do I no longer maintain stability with K? On the far left, eventually, once they re-enter, that one pole that goes off to minus infinity will eventually exit the unit circle, the magenta unit circle, and now I'm stable for K between K box and K triangle. Is that clear? What happens, I guess I'm going a little bit beyond exam number 3. Are there questions? I was going to say, what about this pattern for a root locus? Yes?
Just to repeat, the blue one, the blue circle is to illustrate that if you have one pole inside the unit circle, but the other one's not.
So the blue unit circle illustrates that we don't have both branches simultaneously inside the unit circle. There's nowhere that we have both branches. There's just the one that comes in for a big gain, but the other one's already zipped off towards minus infinity, and it has a magnitude bigger than 1. So the blue unit circle doesn't work. Even if we expanded it, and I included, let me do this a little bit, I'm gonna probably not be happy with this, but what if I did this? Suppose that's now my unit circle, my blue unit circle. Is that now stable? Did I hear a yes? Did I hear a no? Did I not hear anything? I'm going to have to speak up. Is that stable? I have 2 branches and they're inside the unit circle, but not at the same time. They're not simultaneous, are they? The one on the right is for small k. It's just now leaving that open loop pole, and then I leave the unit circle with both of them as I crank up the gain k, and then what? I keep cranking up the k, but I can only get one back into the unit circle. So there are no 2 branches that are simultaneously inside the blue unit circle, and so my result here, never stable, still is valid. It's never stable. That answer your question on blue? So we had yellow, which is hardly visible. That was never. Blue was never, and magenta was yes. And magenta had a particular range of values for stability. And do you see that I could kind of do the same with the right-hand side? Depending on how those are organized or arranged, you could have different possibilities for stability with the right-hand picture. What about this? Can you cut the bread at least? What's our pole zero excess? 3. We've never talked about a 3, have we? Yet. We will, but that won't really be on exam number 3 because it deals with 3, right? But we can figure out which segments of the real axis belong to the root locus. That's rule number 2, isn't it? Which segments belong to the root locus? Here. Between the rightmost pole and plus infinity? Is that on the root locus? No. How many branches of the root locus do we have? In total, how many branches of the root locus do we have? I need to put my glasses on in order to see across the room. Okay, just checking. 3, right? We have 3 poles. We have 3 branches. I've drawn 2 branches with just that one segment. Where's my third branch? Between the left 2? No, it's from the left one all the way off. What's my pole 0 excess? 3. So how many branches are going off to infinity? 3. In fact, what we will learn is that these branches will go, we've got one of the 3 going off to minus infinity on the real line. The others will show that we look at the fundamental angle of our asymptotes will be 180 degrees divided by the pole 0 excess. So one of the branches actually goes off here at 60 degrees asymptotically. It will approach that asymptote. We'll figure out where this asymptote line intersects the real axis. That we will call a centroid. And these asymptotes will be symmetrically dividing this entire z-plane into different pieces. Do you see that I now have 120 degree wedges? I have 60 degrees up, I have minus 60 degrees down, and 120 degrees from either of those is my third, but these will now, these 2 will come together, and one will go up here and approach that asymptote, and this one will come down there. Where do you think they break away? Could you find that breakaway point? Yes, that's rule number 3. That's at a relative maximum between those 2 poles. If you've plotted K values between those right 2 poles, you'll see that on the real line there is a relative maximum, and that would be where they break away. So if I gave you a chart or a table of z values and K's, you should be able to circle where the z is, where the K is maximum, and that would be the breakaway point.
It won't be the average of the 2?
It won't be so the breakaway will not be the average of the 2. The breakaway will be influenced by that other pole to the left. And the reason it's not is because we have 3. If the average works if we have that. Now the average of those 2 poles will be the breakaway, and our asymptotes will be at plus and minus 90. That's 180 degrees divided by the pole 0 excess, and those asymptotes will be exactly splitting. No geometric, this is the arithmetic mean between those 2 poles. Maybe I didn't draw it that way, but that's pretty close. That's now the average between those 2, or it's the midpoint between those 2 poles. And this angle is 90 degrees, which was 180 divided by the pole 0 excess, which is 2. And the pole 0 excess tells us how many branches we have going off to infinity. One's going up and one's going down, and they're going at plus and minus 90 degrees. And again, this one you should be able to draw on exam number 3, because it's just incorporating the first 3 rules. The poles, the line segment, real axis line segment, and the breakaway point. And the breakaway point here is midway between those 2 poles. Questions? prior to exam number 3? Speak now or forever hold. Yes?
So back on your second one that you drew, you had 1 pole, 1 0 inside the unit circle.
Mm-hmm.
What's the K range? Stable for all.
So now the question, I think, concerned one of my very first plots in the root locus. What's the range of K for stability? All non-negative K, right? It's from K greater than or equal to 0 and less than infinity. Because as you get to infinity, you're getting to that finite 0. So that one is an easy one in terms of, but maybe it's hard because you're going, wait a minute, which K's? Yes, where does it end? It doesn't. You can just keep cranking up the K, but now that closed loop pole is going to be getting right on top of that 0, and your system really won't have much response. Because now your closed loop pole is getting canceled by the 0. So it's kind of a, well, K big isn't probably what you want, but it's valid in terms of stability. So depending on what you're asked, any K, as long as it's positive, will work for that particular root locus shape. I'm talking about this root locus shape there. And maybe I shouldn't circle that because now they're going, how do you get a unit circle that's plus and minus 3? It's not a unit circle anymore, is it? The unit circle is bounded by a radius of 1. Do you see how all of these ideas are starting to come together? I hope. That's what I want to happen by this exam and obviously the final. The final is going to be comprehensive. But now we're starting to look at these root locus patterns to give us a feel pictorially what's happening to closed loop poles. Other questions before we shut it down? You should be getting a pretty good handle on sketching these very basic root locus patterns. I don't see any hands, and I've blindfolded myself, so I'm not seeing any more hands, even if they are up. Good luck on exam number 3.